Hello and welcome to today's lesson on uncertainties in the practical skills aspect of the A-Level Physics course. In today's lesson, what we're going to do is we're going to look at what uncertainties are and understand why we have uncertainties in experimental values. So if we're successful and we learn in today's lesson, we understand the importance of uncertainties, we can determine the absolute and the percentage uncertainties in values, and then finally we can calculate combined uncertainties in values, which falls into the following part of the A-Level AQA Physics specification. Now, overall, at least 15% of all marks in the A-Level Physics courses require the assessment of practical skills. Now, for AQA, the majority of these marks will be found on the A-Level Physics Paper 3. Now, in order to be able to answer these questions, students need to have been taught and have acquired competence in the appropriate areas of practical skills as indicated in the table of coverage on the screen. Now, over the next few lessons, we're going to look at the different types of questions which can assess your understanding to these practical skills and how to answer these types of questions. Now, like a GCSE, there are several required practical activities, 12 different investigations, but unlike the GCSE qualifications, questions are not likely to be based on these practical activities. So it's important we build up your competency in each practical skill so that you can apply these to different applications and experiments. Now, in today's lesson, we're going to look at how to calculate uncertainties for measurements taken in investigations. Now, in any value measured, there's always some error in the measurements. Now, this is because there is at least some uncertainty in the measuring devices used to measure variables. So there's an uncertainty due to the measuring device, e.g. used in the stopwatch. Now, this is determined by set rules which govern all measuring devices, but in addition, there may be more uncertainty placed on this reading due to an experimental error. So, for example, reaction time. Now, the uncertainty placed on the measurement reading is a combination of both factors, and we call that the error. So the overall error is the uncertainty in the measuring devices, which we can work out with set rules, plus the uncertainty in the experimental technique, which you estimate based on your own judgment. Now, in our results, we must always write down a numerical value of error in each experimental value. Now, the error gives a range of values the measurement must lie in. So, for example, 2.5 plus or minus 0.1 volts means the value could be between 2.4 volts and 2.6 volts. So let's look at this particular example on the screen. Potential difference is equal to 10 volts plus or minus 2 volts. This means that you're very confident the result lies within 10 minus 2, 8 volts, and 10 plus 2, 12 volts. So the measured value you may have been was 10 volts, but we think the actual value is in the range between 8 volts and 12 volts. We're very confident that the value must actually be in, when all things are considered, between 8 volts and 12 volts. Now, the value should always be presented in this particular format, and the range of possible values takes into account the mistakes made in your experimental technique and the resolution of the measured device used. Now, you can write your answer as an absolute uncertainty, which is just a numerical value. So, for example, 10 volts plus or minus 2 volts. So there's your absolute uncertainty, but you can also write it down as a percentage of the experimental value, which is what we call the percentage uncertainty. So you could have, for example, 10 volts plus or minus 20%. Now, in any scientific investigation, you must write down your experimental values with an uncertainty, either absolute or percentage. So you should never just write down a value without uncertainty in your thorough scientific analysis. Generally, you can write your uncertainty, which you will give with your value, as either a percentage or an absolute. However, there are some situations where it's better to write one or the other. Now, previously, when you've taken measurements in a results table, you'd have illustrated it as the following, with a quantity measured and a unit of quantity. Now, you've also got to include uncertainties in your experimental table headings. So now we write down what our uncertainties are in our measurements in our results table. But how do you determine what the uncertainty is? Now, every measurement has some inherent uncertainty. Now, the important question to ask is whether an experimenter can be confident that the true value lies in the range that's predicted by the uncertainty that is quoted. Now, good experimental design will attempt to reduce the uncertainty in the outcome of an experiment. The experimenter will design experiments and procedures that will produce the least uncertainty possible and then allow you to produce a realistic uncertainty for the outcome. Now, in assessing your uncertainty and trying to work out a realistic value, there are a number of issues you've got to consider. The resolution of the instrument used, the manufacturer's tolerance on the instruments, the judgments that are made by the experimenter, any procedures that you adopt, for example repeated readings, and the size of the increments available, e.g. the size of drops from a pipette. Now, a combination of the above factors means that there's no hard and fast rule about the actual absolute uncertainty in a measurement. However, there are 4 different ways we can calculate absolute uncertainty in a value. Now, Method 1, calculating uncertainty due to the measuring device used. Method 2, calculating uncertainty due to the experimental technique. Method 3, calculating uncertainty due to a stated value given. And finally, calculating uncertainty due to the variation in readings. Method 4. Now we can assess from an instrument's resolution the minimum possible uncertainty. So in Method 1, we can only ever work out the lowest possible uncertainty. Only the experimenter can then assess the other factors based on the arrangement and the use of apparatus, and a rigorous experimenter would draw attention to these factors and take them all into account to then work out your final absolute uncertainty. Now, once the absolute uncertainty has been calculated, we can then work out the percentage uncertainty. Now, you tend to find that when questions use the term uncertainty, they refer to absolute uncertainty and not percentage uncertainty. So you would only calculate percentage uncertainty when a question explicitly states the phrase percentage uncertainty. Now, absolute uncertainty can only be reduced by improving your experimental technique or by carrying out repeats of your results. So we're now going to review the first method for calculating absolute uncertainty, which is calculating uncertainty due to the measuring device used. Now, you should know, like we mentioned before, that every measurement has some inherent uncertainty due to the measuring device. So there are set rules used in determining the uncertainty due to a measuring device, and this is based on the type of values which are taken, which can be split into 2 types. The first type is a reading. These are values found from a single judgment when using a piece of equipment. So that's when you look at a device once to take a value. So for example, these values only require one judgment from the equipment. So when you're measuring the mass of a beaker with a balance, you only look at the balance once. So this makes it a reading. So if you've got to look at a device once to make one judgment, you have a reading. Now, also you have measurements. Now, these are values taken as the difference between the judgment of 2 values, i.e. you look at a device 2 times to take this particular measurement. Now, an example of this would be when you are measuring the length of wire with a ruler, because you're looking at the ruler twice, at the start of the wire and at the end of the wire. So 2 judgments is a measurement. Now, as a general rule, the type of value can be split from a reading and a measurement into the following situations due to their measuring device. However, readings will only need 1 judgment, 1 look from the experimenter, while a measurement will need 2 judgments or 2 looks from the experimenter. Now, the uncertainty in a reading when using a particular instrument is plus or minus half of the smallest division. So, for example, a temperature measure with a thermometer is likely to have an uncertainty of plus or minus 0.5% if the graduations are 1 degree Celsius apart. 0.5 degrees. Sorry about that. Now, that's because in a reading, when you only look at a measuring device once, the absolute uncertainty is half of the smallest division. And because the smallest division in a thermometer is 1 degrees, that means our absolute uncertainty is plus or minus half a degree. So this is because you're only taking 1 value from the device. So let's think about this logically. So if, for example, you were looking at this value and you could say it was 30, well, if you had that same scale, that would be the case if it was anywhere between 29.5 and 30.5, because you'd round it to 30. So we know that any value between 29.5 and 30.5, because we don't know any better from our resolution, has to be rounded to 30. We can say the absolute uncertainty is 30 plus or minus 0.5, which indicates why for a reading it's always going to be half of the smallest graduation. Now, you should always ensure that the value and the uncertainty are given to the same amount of decimal places. This is because you can't have the uncertainty more or less sensitive than the answer stated, because this therefore means your confidence is then consistent. So actually it should be 30.0 plus or minus 0.5 degrees Celsius. Now, when measuring measurements, you take two judgments. So there are two uncertainties. So as both judgments have an uncertainty of plus or minus 0.5, half of the scale, this means that the overall measurement, because there are two of them, will be plus or minus 1 of the division. So therefore, in a measurement, it is going to be plus or minus the smallest graduation, the smallest increment of your measuring device. So for example, a temperature change, which is a measurement because you're looking at the thermometer twice, okay, is likely to have an uncertainty of plus or minus 1 degree Celsius if the graduations are 1 degree Celsius, as we have two judgments being taken. So therefore, the uncertainty of a measurement is the same as the smallest scale division, because if one look is plus or minus a half and the other look is plus or minus a half, well then together it's going to be plus or minus 1 whole division. So when measuring length, for example, two uncertainties must be included: the uncertainty of the placement of the zero of the ruler and the uncertainty of the point from where the measurement is taken. So as both ends of the ruler have a half scale division uncertainty, the measurement will have an uncertainty of one scale division. So this means for most rulers, this means the uncertainty is the measurement of length will be plus or minus 1 millimeter, because that's the scale of your ruler. So we can summarize the rules for absolute uncertainties with the following statements. The uncertainty of a reading, which requires one judgment, is half of the smallest scale division, whilst the uncertainty of a measurement, which is two judgments, is plus or minus 1 of the smallest scale division. Now, the second method to calculate absolute uncertainty is calculating the uncertainty due to experimental technique. So let's have a look at that particular methodology. Now, this is where you've got to include some uncertainty due to the experimental technique or the human experimenter. Now, this should be added on to the measuring device uncertainty you calculated previously. So for example, a stopwatch has a resolution of plus or minus 0.01 seconds due to the measuring device, because it is taking a measurement and that is what its smallest increment is going to be. But the uncertainty in the measurement is more likely to be higher due to the reaction time of the experimenter. So this must be added onto the absolute uncertainty of the measuring device to give a larger uncertainty value. So if you think the experimenter causes more uncertainty by carrying out the measurements than the device produces, you must state this uncertainty and not the measuring device uncertainty. So another example would be if a student measures the length of a piece of wire, it's very difficult to hold the wire completely straight against the ruler. So the uncertainty in the measurement is likely to be higher than the plus or minus 1 millimeter uncertainty of the ruler due to its resolution. Now, this is dependent on the number of kinks in the wire. It could actually be plus or minus 2 or 3 millimeters. Now, when we're trying to work out this value, this experimental error uncertainty, you've got to estimate it. There's no one right answer for estimating this value. It's down to your discretion, but it's just got to be reasonable and sensible. Another example could be the uncertainty of reading from digital voltmeters and ammeters depends on the electronics, and it's not going to be the last figure in the readout, as the value can fluctuate greatly. So you've got to estimate this uncertainty due to the fluctuation, and there's no right answer for this. It's an estimation. Another example would be when timing a pendulum swinging or a spring oscillating. The stopwatch will have a resolution and therefore an uncertainty of plus or minus 0.01 seconds, because it's a measurement, because we're looking at it twice. However, the human reaction time to carrying out this timing is going to be much larger than this resolution. It could be plus or minus 0.5 seconds. So we've got to add this on to our uncertainty when we calculate it through. Now, the third method is calculating the uncertainty due to a stated value given. Now, if you're given a value from a data sheet or in a question, you still got to consider its uncertainty. Now, in these situations, we assume the uncertainty to be plus or minus 1 in the last significant digit. So the value of the charge of an electron is given on the data sheet is 1.60 times 10 to the minus 19 coulombs. So we look to the last significant digit, which is 0. So we then say it's plus or minus 1 of that significant digit. So therefore, the uncertainty in this value is plus or minus 0.01 times 10 to the minus 19 coulombs. Now, the uncertainty may be lower than this, it may be higher than this, but without knowing the details of the experiment and the procedure that led to the value being calculated, there's no evidence to assume otherwise. So you've got to consider the uncertainty in every value you're given in an investigation. So here's an example of this. If the number of lines per meter is quoted as 3.5 times 10 to the 3 per meter, it's then usual to assume the uncertainty is plus or minus 1 in the last significant figure or digit, so therefore the last significant figure or digit is 0.5, so therefore it's plus or minus 0.1 times 10 to the 3. Now again, it might be different to this, but we don't have enough information, so we assume this particular practice. Now we can write it as either engulfed inside of the 10 to the 3, or we can have it outside. Either representation is suitable. Now the fourth way to calculate an absolute uncertainty is calculating uncertainty due to the variation in readings. Now if you've got repeated values and you've derived a mean, then the absolute uncertainty can be calculated from the variation in the repeated results. Now this comes from the idea that the maximum possible value for the results is the largest value of the repeat readings, and the minimum possible value for the result is the smallest value of the repeat readings. So when looking at the variations in reading, you've got to remove the anomalous results first. Then what you do is you find the range. So you take your biggest value, you take your lowest value, you subtract one from the other, and that is your range. Now this means the value must lie within the middle of these limits, and the uncertainty must extend to the highest and lowest value. So this means we can work out the absolute uncertainty by taking the range and dividing it by 2. So in this example, the range is 0.10, we divide it by 2, so it's plus or minus 0.05. Now this happens because you're confident the value lies between the highest value recorded and the lowest value recorded. Now in an investigation where repeats are taken, the experimenter is confident the true value lies between the highest repeated value and the lowest repeated value. So the middle answer is going to be the most likely outcome in between the highest and the lowest value. So therefore, as we're confident the answer lies between the range, we can state the absolute uncertainty is half of the range, which allows the full range to be represented when we use the plus or minus symbol. It's half the range. Now this method reduces absolute uncertainty as repeated results, until you gain concordance, means that anomalous results can be discarded, leaving a small range of data. Now can I also state that the range of data is also called the precision at A level. So how precise your data is how big the spread of your range is. If you've got a small range of data, you have a high precision. If you've got a big range, a big spread of data, you've got a low precision. Now, in this example, we're confident the answer lies between 1.80 meters and 2.00 meters, because that's the biggest and the smallest value of our repeats. So therefore, we look at the range, which we know to be 0.20. We then divide it by 2 to get our absolute uncertainty. So we state the value is halfway between the middle and the lowest and the highest, which is 1.90 plus or minus half of the range, 0.10 meters. Now we can calculate the percentage uncertainties from the absolute uncertainty once we've calculated the absolute uncertainty with the following method. We can say percentage uncertainty is the absolute uncertainty divided by a measured value times by 100. If you'd use repeated measurements, percentage uncertainty is equal to the absolute uncertainty divided by the mean times by 100. Now again, the absolute uncertainty for repeated measurements can be worked out from our previous methodology, and it's good practice to reduce the percentage uncertainty to the lowest possible values. Now a way to reduce the percentage uncertainty is to use the largest values possible, because if you're dividing by a larger number, if your absolute uncertainty is constant, it's going to give a smaller percentage uncertainty. Or if you try to reduce the absolute uncertainty, you could either carry out repeats, you could improve your experimental technique, or you could use measuring devices with the smallest resolution available. So an example of a percentage uncertainty calculation is as follows. If we have a value which is 10 amps plus or minus 0.1 amps, so we take our absolute uncertainty 0.1, we divide it by our value 10, we then times it by 100. Okay, so we go 0.1 over 10 times by 100 is 1% or 1.0%. So our value is 10 amps plus or minus 1.0%. Now again, remember, when stating the percentage uncertainty, we don't need to have a unit because it's a percentage. Now, when dealing with different formulae and equations in physics, we have uncertainties from different values. So we've got to combine these uncertainties to find the overall uncertainty of a value. Now, this is the overall uncertainty of a calculated value based on the uncertainties in the values needed to calculate it. So, for example, if we wanted to work out the uncertainty in the power, and we know power equals potential difference times by current, we've got to consider the uncertainty in the potential difference and the uncertainty in the current, combine them in some way to work out our uncertainty in the power. Now, there are several rules to follow depending on what equation you use to calculate a value. Now, when you have a addition or a subtraction, you've got to add the absolute uncertainties. So an example of this will be extension. Extension is stretch length minus original length. So it's a subtraction. So in that instance, you add the absolute uncertainties. So if the absolute uncertainty for one value was plus or minus 2, and the uncertainty in the other value is plus or minus 1, to find out the total uncertainty, it's 2 plus 1, it's plus or minus 3. Now, if you have a multiplication or a division, what you have to do is you've got to add the percentage uncertainties. So, for example, resistance is equal to potential difference over current. So if you wanted to work out the overall uncertainty in the resistance, and we knew the potential difference had an uncertainty of plus or minus 4%, and the current had an uncertainty of plus or minus 3%, we would say the percentage uncertainty, in the resistance, the overall percentage uncertainty is 4% plus 3%, which equals plus or minus 7%. And that's the same if it's multiplication or it's division. And then finally, when we think of an equation which has a power in it, so for example, area is equal to pi r squared, we multiply the percentage uncertainty by the power of the value. So for example, we know that volume is equal to length cubed. Now, if we know the percentage uncertainty in the length is 2%, and the length is being cubed, so the power value is 3, so the percentage uncertainty in the volume is 2% times by 3, the power value, so it's plus or minus 6%. So if the quantities in the equation contain a power, like a squared for example, then you multiply your percentage uncertainty by the power value. So we can summarize our ideas of uncertainty with the following. Uncertainties is a measure of how certain you are of a value. If it's in the range, it's the range of values you're sure a result lies in. The absolute uncertainty can be calculated by absolute uncertainty is equal to value times by percentage uncertainty divided by 100, whilst percentage uncertainty is the absolute uncertainty divided by a value times by 100. The term uncertainty tends to refer to absolute uncertainty, not percentage uncertainty, and there are 4 methods to calculating the absolute uncertainty in a value. Method 1, calculate the uncertainty due to a measuring device used. It's the resolution of the device if it's a measurement. It's half the resolution of the device if it's a reading. Method 2, you can calculate uncertainty due to experimental technique, which is an estimation you would make. You can Method 3, calculate the uncertainty due to a stated value. That's plus or minus 1 of the last significant figure of the value. And Method 4, calculate uncertainty due to variation in readings, which is the range of repeated values divided by 2. We can then combine uncertainties when we've got more than one uncertainty in a calculated value. Now, if you're adding or subtracting a value in a calculation, you've got to add the absolute uncertainties. If you're multiplying or dividing by a value in a calculation, you've got to add the percentage uncertainties. And then if you're using values with power, you must multiply the percentage uncertainty by the power. Now, we can use our calculations of absolute and percentage uncertainties to make 2 conclusions. Conclusion 1, the validity of the experiment. Now, if your percentage difference is smaller than your percentage uncertainty you've calculated, we tend to believe the result agrees with the theory or we verified the experimental value. And conclusion 2, we can use this to determine the major source of error in your investigation. We find the highest percentage uncertainty of the measurements taken and try to decrease this value in future experiments. So like we mentioned before, we can reduce the percentage uncertainty in a value by either increasing the size size of the value, so use larger numbers, or by using a device with smaller resolution, or by repeating and taking a mean average, or by improving experimental technique. It's more common in investigations. The easiest way to do this is just to use larger values. So in this lesson, you should be able to solve problems set in practical contexts, apply scientific knowledge to practical contexts, and evaluate results and draw conclusions with reference to measurement uncertainties and error. So if you've been successful and you've learned in today's lesson, you understand the importance of uncertainties, you can determine absolute and percentage uncertainty in values, and you can calculate combined uncertainties in values. I hope you've enjoyed today's lesson looking at uncertainties in the practical skills aspect of A-Level Physics, and have a lovely day.